This. Oh, did I already hit record? Or is that just new wording? I got this morning. I turned on my Zoom and I did an upload, so maybe that's just a new phrase. Uh, Anyways, I got the recording going. All right, so I'll just start here. Okay, it looks like Anthony, you're first here. Chapter 16. Oh, number 58. So that sounds like a big one later on. All right. So let me write on my paper here. Chapter 16, number 58. Let me do a screen sharing. And share my camera. Okay. Give that a second to swirl around. Looking good. Okay. And nice. There's a small delay.
It's
Well, I guess
not.
this is good.
Yeah, it's not so much as the delay as it is lagging. That's better now.
Yeah. So maybe it'll catch up. All right. All right. So then let me. Well, I don't think I've ever seen that before either. I was going to switch over to the questions and went to miniaturize Zoom, and it goes, you cannot miniaturize Zoom when you are recording. Okay. Let's see if I can put it on top. Okay, good. I can do that. All right, so let's go to the question. Oh, yes. Probably because it says a little bit of calculus. Oh, and by the way, will it be okay? I should have looked because I was reading this one this morning and I noticed that part A or part B, it says show that this reduces to the same thing you got in 57 when capital M is equal to 0. So these almost go together. Let me go back to the Zoom. Did anybody want to see 57? Should I do them both?
I would like to see 57 if you're going to go over the other one.
Yeah, it'll take a little longer, but I think it's worth it. So let me do that. Let me do number 57 here. And then, so let me cross this out. And then we can, and they're almost identical in the way that you do them. The equations are a little different, so the calculus and the math come out a little bit different. So let's go back to 57 here. And 57 says this. It says a rope of total mass little m and length L is suspended vertically. All right, so I'm going to try to make like a ceiling. I'm going to put a rope hanging down here at the bottom of the rope. Let me call this position X equals 0. And then so we go up and the whole length of the rope is L. Suspended vertically. Show that the transverse pulse travels the length of the rope in this time interval. So in other words, it was saying if down here, maybe you wiggled it to one side and you made a little lump, that lump is going to travel up. And its speed is varied upon its tension. Okay. And so its tension, though, is decided by, let's see, transverse pull, suspended, show that it travels up the length in a time interval. And then the suggestion here, it says First, find an expression for the speed of wave at any point distance x from the lower end. Okay, so good. They say lower end because that's how I set it up. But one of the things that hopefully you got out of the reading here was that the velocity is the square root of the tension over the mass density. Now, in our case, the mass density is pretty easy. It's just the mass of the rope, which they called little m, and the length of the rope, capital L. Okay. But the tension really takes us back to physics 121. It takes us back to, maybe I'll just grab some random point in the middle of the rope and do a free body diagram with it. And so I'll pick that little point right here. Because at this particular point, there would be below it all this mass. Now, it's not the whole mass of the rope, it's only part of it. But the tension then would have to be pulling upward here. That would equal the mg. And I hesitate to write little m because it's really just a piece of it. So maybe I should write it a little different. Maybe I should write it as m prime. That looks like kind of like a derivative. Maybe that's a bad choice. M1. All right. For lack of better options, I just wanted to point out then that this would be some kind of mass that's below this point. It's not the mass that I use down here for the total mass of the rope. Okay. So with that in mind, let's see if we can figure out what that mass would be. And if this distance up is x, we could probably do this easiest by just setting up a proportion. That would, you might say something like this, that the mass below this point, m1, compared to the total mass, m, is the length below this point, L, times the total length. And so m1 becomes m over L times x. In fact, now that I write it this way, it even might have been easier to figure out m1 by saying it's the mass density, which they write as mu, times the length of the piece we're looking at. And the piece below that point is x. And then I could have wrote little m L x. That might have been an easier way to get m1. But in either case, I'm trying here to get an expression for the weight below this point, and then write it in terms of x, so I have it at any point along this rope. And so the bottom line, and what makes this problem a little harder with the calculus, is that the tension keeps changing as you go up. And so they put review problem on here? Because the tension part of this is definitely physics 121. No, they didn't.
Hi, how you doing? Hello? Can you hear me?
Hello?
Hi, Professor Young, can you hear me?
Yeah.
Hi, Elizabeth here.
Hi,
What's the goal of the exercise? Are we looking for tension at different lengths of the rope?
No, the goal of the exercise is to ultimately find the time it takes to go from the bottom of the rope to the top.
Okay, so can we just, why are we finding the mass? How does that relate to the time?
Oh, well, okay, so maybe I should have kind of showed a little more where I was going. The time is related to the velocity. The velocity is related to the tension. and the tension is now going to be related to the mass below it. So that's why I'm starting there.
Okay, so these are segments, individual segments, or do the segments like add up and it's cumulative?
Let me take your hang on to this. Let me go the direction that you're kind of asking here, and that is we'll call this page 2. Let me go back to physics 121 here for a second, and write velocity equals the distance traveled over the time taken. So dx. Oh, and let me just pause a second. I've got a little delay on my video feed. Do you guys have that too?
Yes, I'm working on a 5-second delay.
Okay. Oh. Okay. Let me turn that off. But that was weird. My laptop kept going, but my desktop kind of froze on me and lost the connection. Did you guys get that? And then, oh. All right.
I just see a
Now
little bit of lag, but it looks like it's working, I guess. Yeah.
Huh.
Yeah. I might. I just got to reconnect my phone. Hey, hang on here. I'm going to stop sharing. See if we can fix this a little bit. And I'm going to reshare my phone. I know in the past that's kind of fixed things up a little bit. So let's reconnect the Bluetooth. And I'm going to move my pen right now. 1,000, 2, 1,000, 3. So I do have about a 3-second delay. Huh. Well, I'm going to try to live with it here for a second. Tell me if it gets too bad, okay, guys?
Hi, it's not too bad for me.
Okay. All
You had left off relating velocity as a rate of change.
Okay. So here's what I was trying to answer for you, Elizabeth, was this, that if I solve the equation of velocity for time, I get this. A little bit of time is equal to a little bit of distance divided by its velocity. Okay. So the total time, t, would be an integration of all these little times added up. This is where the calculus comes in. So this would be then an integral of a little bit of distance over velocity. And this is why I had started, and I didn't really explain, so I'm glad you're asking, Elizabeth, why I'm bothering to figure out the equation for the velocity back on page 1, and that's because right here, this integral I need to do, and velocity changes with position. I know that, going back to page 1, because velocity depends upon tension, and tension depends upon the position of that rope. So
So velocity is related to tension and as well as the space.
yeah, I would say it's not as well, but I would say tension depends upon the position.
Right.
Yeah. Okay. All right. So I kind of like the approach you've kind of made me go down here, because this is the big picture. The big picture is, to get the time, I need to integrate this little equation here. And this is where the physics, 121 comes into play. Uh-oh. Now I think it completely froze. Still having technical difficulty. Well, bummer. I rebooted everything right before, so I wouldn't have such a problem. But I'm going to try it again here. Let me. And actually, when I was rebooting everything and practicing this morning, it downloaded a new version of Zoom here. Oh, okay. Well, now I'm back with no delay. So, all right, I'm going to keep trying this. Bear with me. I apologize. All right. So the big picture for Elizabeth and everybody else is right here. Now, here's what I'm trying to do. I'm trying to find the total time. And to do that, I need to add up the times as it goes up from the bottom of the rope to the top. And I'm trying to then write that as an integral with position. And so now I can put together what I was doing over here on page 1. So let me do that now. This would be the square root of the tension divided by the mass density. And then this integral would be dx, the square root of, I'll just leave the mass density alone here. But as I was trying to say here, is the tension then would be this M1G, M1 being the mass below some point X on the rope. Then, as we worked out down here, M1 is the mass density times X. And so divided by mass density. So I'm going to use this that we kind of worked out back on page 1. This will give me a chance for the mass density to cancel out. Then I have an integral of, let's see, dx, and it looks like I've got the square roots of x. Let me write that as x to the 1/2 power, but then let me move it up so that it's in the numerator. So it's x to the negative 1/2 power dx. Now let me actually do the integration. And when you do a power function, you add 1 to the exponent. So a negative half plus 1 is 1/2. Then you divide by the new exponent. And now I should probably put in my limits. I'm integrating this pulse from the bottom. And so that would be x equals to 0 to x equal L. So I would go from 0 to L. And so I guess technically this should have been in all the little integration symbols, 0 to L. So then I have, let's see, I'll take that 1/2 and just put it as a 2. And then I would have the limits here. This would be L to the 1/2 minus 0 to the 1/2. And so this would be written as 2.
See there, he's finally answering my question. That's good.
I think in all this technical confusion, though, and I apologize, I dropped an M somewhere.
Yeah, you dropped the M, I think about the third or the fourth line.
Oh, okay. My bad. Now I see it. It wasn't an M, it was a G that I dropped. Let me come back here. Everything I did on the first page was right, but then see the tension should have been M1G. And back here, I put the MG, but then when I went to this line, I just had the M. So there should have been a G there, which would have made a G there, which would have left a square root of G there, which would have left a square root of G there.
Thank you.
Okay. Which would have left a square root of G. And so 2, and I'll just put this in one big thing as the square root of L over G. And so again, apologize for the technical difficulties. I probably threw me off a little. But that should be the answer to 58. In fact, I'm going to, now that I kind of messed it up here, let me jump over to the solution that your author has given you. Where are these solutions? And let me go back to 50, what is it, 57? Okay, good. So the author and I agree that this is the solution. Okay. All right. So with that in mind, unless you guys have a question on that one, I can finally get to your real question. I believe it was Anthony who asked this. Let me write down 58. And I'm going to kind of do the same thing here. So it's probably good to see it again. And so let me just put number 58 for anybody who later on is going to kind of want to scan the video here. All right. So in 58, it says, do this. Assume that an object of mass capital M is suspended from the bottom of the rope in number 57. So that's why I know you guys asked about 58, but I felt like I needed to start with 57. So I'm going to draw a new picture. I'll call this again page 1. Let me make this kind of the ceiling. Let me draw a rope coming down. And this time, what we're going to do is put an object at the end. And the object has a mass of capital M. So the mass of capital M is suspended at the bottom of this rope. And the implications of that is that the length of the rope is still length L and still has a mass of M. And so repeating maybe kind of quickly what we did in 57, is to remember that velocity is distance divided by time. It's actually the derivative of distance and time. Okay. And we rearrange this to say then a small moment in time would represent a small distance divided by the velocity. So if we were to, hit this weight down here at the bottom, which makes a little pulse, the pulse would travel upward. But the tension would change as we go up the rope. And because of that, the velocity would change. So, like we did in 57, to talk about the total time, we need to add up dt's. We need to add up the little time segments needed to go up this rope. Okay. And we can write then this little dt as a dx over the velocity. And of course, what makes this a hard problem then is that the velocity keeps changing as the pulse goes higher and higher up the rope, the tension gets greater and greater and greater and greater. And so that's, of course, what we saw in 57, and we're going to see it here. And again, I'll just keep going with this. So this would be a dx, and it would be the velocity would be the square root of the tension divided by the mass density. Okay, so here's where I need to, pause from our current class, Physics 123, and say, okay, well, how do I get the tension at different points in the rope? And now if you remember back on number 57, I just picked a random point, some distance x up the rope, and looked at how much tension, saying the tension pulling it up has to equal to all the weight below it. Okay. So in this case, if I just draw a line and I'll come over here and maybe draw that little section of the rope.
Dr. Young, you have frozen. Oh. And he's gone.
Yes, he's back now.
You're muted, Dr. Young.
Mute. Okay.
Here you go.
Oh, okay, that was weird. My Zoom flashed and said disconnected, reconnecting real quick there. Huh. Okay, but I'm back. Okay.
One thing I did notice is that on the videos it splices everything together smoothly. So even if it freezes like here, it splices things together pretty smoothly.
Good to know. Yeah, okay, good. I did not know that. Okay. So that little glitch will be spliced out, hopefully, or okay. And it looks like it stopped my sharing when it did that. So let me go back to share my screen. All right, let me get my phone connecting. Okay. All right. So what I was trying to draw over here when the disconnection happened was that the tension at this point, so pulling up would be the tension, would have to be equal to all the weight below it. And all the weight below it then would be the mass of this hanging weight, so capital MG, but it would also be this small amount of the rope, which in the last problem, I labeled it as M1G. Okay. So let me then, now I'll make one more line before we come back to where we were working. So this is capital MG. And what we came up with is that the mass below this would be the mass density mu times the distance x. And there's that g that hopefully I won't forget this time. And so that would be the tension. All right. So continuing on with this integral, there's the dx. I would have then the square roots. And so for the tension, I would have capital M times G plus mass density times, I'm going to write G first and then the X. And then, of course, over the mass density. And so I'll say it again, it was this kind of step here that kind of made me wonder if this would be labeled as a review problem. It's not, okay, but this is the tension as it varies with the length. And of course, what's important for this semester is to know that the velocity depends upon the square root of the tension. And of course, what's also a review from last semester, or 121, depending if that was last semester or 2 semesters for you guys, is that the time here. Okay, so this is very much like, in fact, if I pull up the second page from problem 57 that we just did, you'll see we essentially have the same equation here as we have here, except we don't have this extra term because we didn't have the extra weight hanging. So that's why 58, I think, is a little harder because it's got that extra term. But the logic is certainly the same, and that's what I hope you're seeing. Now, maybe I will simplify this a little bit. This denominator is a compound fraction. So I'm going to write the square root of mu up at the top. And so that I then have a dx. And in the bottom, I have the square root of mg plus the mu, the mass density, times g and x. Okay, so I'll just rewrite that compound fraction. And so now I have to actually do the calculus part of this, and so I have to do this integral. Now to do this integral, I think this might be best done by a u substitution. Now I'm hesitating a little bit because a u might look like a mu. So I'll call it a u sub, since that's how you probably learned the name in your calculus class, but let me give it a different symbol. What might be a better symbol? U, the next letter in the alphabet's V. I don't want to use that, that's velocity.
Alpha.
I like W. It's 2 U's.
W could look like 2 U's. Yeah, we could go on and on about this. Someone said alpha. All right. So, well, I'll do alpha. What the heck? Okay. So let's do this little step here. Let's say alpha is, and let's call this an mg plus mu gx. Okay. And then when I differentiate it, then d alpha then becomes mu g dx. Okay, so bringing my calculus down here, this is the square root of mu, and now I'll do my substitution. So in the denominator, I'll do the square root of alpha. Okay, so that's that one. And then the dx right here, I'll replace that with, and I got to move this to the other side. So that would be a d alpha over mu g. Let me go on to page 2. All right. Yeah, you guys started the morning off with a tough one. All right. Wake me up. Okay, so continuing on, let me pull things that are constants out in front of the integral. So this would be square root of mu. This would be a mu over g. And then I'm left with a pretty easy integral, a d alpha over the square root of alpha. To maybe simplify this a little bit more, why don't I cancel a little bit? So out in front is 1 over, so this would be the square root of mu, although the g is not in the square root. Okay. And let me write this calculus as alpha to the negative 1/2 power, because again, this would be a square root to the 1/2 power, and I bring it up, it'd be a negative 1/2, and so that would be d alpha. Okay, so then I get 1 over square root of mu, then the g. And now doing this integral, I've got my alpha, and any power function, you add 1 to the exponent. So I add 1 to a negative 1/2, and I get 1/2. And you divide by the new exponents. There'll be some limits. Let me not worry about the limits quite yet. So I'll just put little markers there. Again, let me kind of simplify. This 1/2 would make a 2 up there. This would be the square root of mu and a g. And I didn't want to put limits because I'm going to go back to the x. And so coming back to what alpha was equal to. So alpha was equal to mg plus mu g x. And so all of that raised to a 1/2 power is really what we mean right here, mg plus mu gx. That's our alpha. And so now that I've written it at an x, I could put my limits in terms of x. And so this started down at the x equals to 0. Down here, here's a little pulse. And it's going to go up until it gets to x equals to L. So there's my L. Okay. So 2 square root of mu g. Okay, and so I'll put in the mg plus mu g, and so here's the limit L to the 1/2 minus, and then let me put in x equals to 0, which would just leave an mg to the 1/2. They probably are going to write this with square root symbols. So when I check the answer, let me write this then as the square root of mg plus mu gl minus the square root of mg. Now we could probably do a little simplifying. For example, let me just come back here. This one actually gives us the answer right here. It says show that it is equal to. All right, so we we kind of know where we're headed to. Okay. Let's do a little bit more simplifying. For example, this mu right here, and this one too, for that matter. Maybe I'll write it up at the top, but mu is the mass density of the string. So it is the lowercase m divided by L. Okay, not the uppercase m. So one thing that can get easily confused is the lowercase m and the uppercase m. But remember, I'll go back to page 1, the string mass is lowercase m, where the hanging weight is uppercase m. Okay, so I'm gonna use that here and write this then, and even simplify the compound fraction as the square root of lowercase m over the square root of L. So the square root of mu would be the square root of m over L. Okay, so that's the putting in the mu here. Now, also putting in the mu here, this mu would be lowercase m over L. And there already is an L in here, so that L is going to cancel off. All right. Continuing with my simplification, you can see that each term has a square root of g in it. So I can factor out a square root of g and put it in front here. Then I can get the square root of g and the square root of g and put it out here. And then that square root of g would cancel a little bit with this g, and you would be left with just a square root of g there. And so in this square root thing, we would just now have the square root of m plus little m, or capital M plus little m. And then we would have minus the square root of capital M. I think we're almost there finally. And then we can put all these square roots together. And so this is a 2. We've got one giant square root of capital L and then lowercase mg there. And then square root of capital M plus lowercase m minus capital M. Ta-da! And I think we matched. Let me check. 2 square roots. Yeah, good. So it took a while to get there, obviously. Big problem. Long problem. Really good problem. So I guess that's the idea. The easy ones you guys can do without me, and harder ones you want to see. So, so there's part A. Show that the time interval is this. And then B says, show that this expression in part A reduces to what you got in number 57 when m equals 0. Or put another way, capital M equals 0. Put another way here, if nothing was hanging, so if we set capital M equal to 0, this would be just like a single dangling rope. And that was what we did on our first step when we did number 57 first. So we just had a dangling rope with nothing hanging at the end. So for part B, if I just set capital M equal to 0, I get 2 times the square roots of capital L over mg. And this whole parenthesis thing now just becomes the square root of lowercase m. And then the two square roots of capital M cancel, and we're left with this 2 times the square root of L over G, which is the answer we got in number 57. So yes, it does reduce when you either want to do it mathematically, set capital M equal to 0, or physically say remove the large mass at the end of the rope and just have a dangling rope or a dangling string. I forget which word they used there. Let me go back to 57. They use rope. Okay. So, excuse me. So that's B. Now, we got to be a little bit more creative with C. And C is going to play a little bit on our mathematics here, but it says show that for little m much less than capital M, so little m much less than capital M, the expression for part A reduces to, and they give a little nice expression. But before I even work that out, let's take a moment to just kind of maybe digest what that would mean. This is the part that I would say, you know, if I was kind of reading the math, interpreting the math, here's what I'm really saying. I'll come back to our picture. If we're saying that the hanging mass, capital M, is much, much, much bigger than the mass of the rope, we could essentially say, oh, ignore the mass of the rope. We could say that the rope weighs nothing. And what's nice about that is then back here for the tension, we would have just said that the tension is always just capital M times G. Anywhere along the rope, we're just holding up the big weight. The fact that there's a little bit of rope below that point doesn't matter because the rope is so light. Now, what that would then also mean is that when you wrote down velocity equals the square root of tension over mu, the tension then would be a constant value of capital mg. And of course, what that would mean is you wouldn't have a variation to your velocity. So instead of doing calculus to get time, we could have just done the old-fashioned, probably what you did in middle school or at least high school. You just said velocity is distance divided by time. You didn't have to worry about the calculus part of it because it wasn't varying along the length of the rope. So if I were to cross out the calculus part of this problem and say that the length is L and the velocity is the square root of mg over mu, and then t is the total time, and I move total time over to here, I would go L, and then I would divide it by the square root of mg over mu. This would be then written as an L and the square root of capital M over G. And mu then would go up here. So it would be the square root of mu. And mu would be lowercase m over L. This would cancel one of the L's. So I'd get the square root of L. I'd have the square root of m, and I'd have the square root of capital M over G. And if I put them all together, and I hope I didn't do too much math here, but what I'm trying to get you to see is this would have been a very easy problem if at the very beginning of the problem, they just told me that you're hanging a very, very large mass and ignore the mass of the rope. I would have just gone velocity equals distance divided by time, and I would have got this equation, and that's exactly the equation they want us to come up with. So I wanted you to understand before I actually do the math why this would be the answer. We would know this is the answer because in this case, the pulse going up the rope would just have a constant speed going up the rope. And I don't know if that was so obvious. So I thought I better stop and point out the physics behind the meaning of this phrase. Hey, let the mass of the rope be much, much smaller than the mass of the hanging object. Because if that's the case, then we just have a constant velocity problem. We don't have any calculus. This is just velocity is distance divided by time. And solve for time. And that's what we would get. And so they're trying to show or have you do some mathematics that if you start with this, what I'll call a more exact equation, where it includes the mass of the rope and the mass hanging, that if you start with that, you could either, as we did in B, ignore the mass that's hanging, or what we're about to do in C, ignore the mass of the rope. And so B and C are like special cases. And C is maybe a little bit harder to see, that it's a special case of the mass of the rope is negligible. All right, so with that in mind, let me just transfer this general equation to times the square root of L over mg times capital M plus lowercase m raised to a power of 1/2. So if you'll let me, I'm just going to transfer it, but instead of writing it as a square root, I'm going to write it as a power of 1/2. You'll see why in hopefully just a second here. And then this here would be capital M to the 1/2. And one of the first things you'll notice in what makes this a harder mathematical problem is we can't do like we did in B. Now, remember in B, I said, oh, if we just pretend the mass that's hanging is really small, just set it equal to 0 and see what we get. So if we play that same game here and we say, oh, let's just pretend the mass of the rope is really small, let's just set the mass of the rope equal to 0, we run into a problem of what in calculus we'd call limits. Because if I set little m equal to 0, so if I set little m equals to 0, I get 0 right here. And of course that happens because of the issue of the limits. It would be a L'Hopital's rule. So just setting little m equals to 0, which is what I would do first. And again, going back to B, that's what I do in B. I would just say, look, if the object hanging is really small, just set it equal to 0 and see what you get. And if I do that here, I run into a mathematical dilemma. And I get a 0. And that means the time is 0 time. And that's not a good answer. And of course, the reason for it is, remember, the velocity is the square root of the tension over the mass density. And so this tension, remember, actually had the hanging weight plus the rope. And so if you set the mass of the rope equals to 0, this one goes to 0. That's cool. But you are essentially then also saying the mass density goes to 0, which means the velocity goes to infinity, which then means the time it takes to go up the rope is 0, because you're saying the velocity is infinity. So you can see I've kind of run into a mathematical dilemma. I've got a denominator going to 0. And that's the consequence of just setting this equal to 0. So, all right. So this is why I want to get a chance. Some of you have seen this before. I think we did this quite a bit in Physics 122. Some of you coming from 121 may not have seen this. I think this is the first time we did it this semester, although last chapter we did something very similar to this. We took a Taylor series on a sine function, and we said it would be equal to sine, I'm sorry, the angle, so theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial. And we didn't necessarily call it a Taylor series. What we did is we called it the small angle approximation. And we said anything that's a small angle you raise to a high power, you can ignore. And we said for small angles, then we could just say that sine theta is equal to theta. So we did that for the simple pendulum and a couple of other times in chapter 15. Okay, so I'm going to play the same game because I think this could be done better by expanding it out in a Taylor series. And the first terms that don't go to 0 would be my approximation for the time it takes. See, if the mass truly went to 0, not just small, then of course the time would be 0. So that's the dilemma I'm running into. What I would like to do is expand this out into a long series of something, like A plus B plus C plus D, and expand it out. And I'm guessing here that probably the first term A is what cancels with that. And then the B, what's left over from the expansion of this, would be the first non-canceling one. And this would be the one that would be relevant for masses that are really small, not 0. So by setting it equal to 0, I'm taking this idea too far. I'm taking the idea that M is not just really small, but I'm taking the idea that it's 0, and I'm running into problems. So I need to do better. I need to say M is not 0, M is small, and I want to see how that works out. So let me do that. Now, this is how I'm going to get around this math problem. I'm going to do an expansion on that. And again, you guys who went through 122 probably remember doing those. For those of you who just came into this class, let me point out that Appendix B of the survey does a lot of these expansions. And they do the sine expansion, and they do this expansion. We call it the binomial expansion. And we did it a lot in our electric fields. And so I'm going to do it again here. So in the interest of maybe not taking up too much time, and maybe encouraging you to either work this out yourself or definitely just Google binary expansion or go to Appendix B in Survey. When you expand this out, a Taylor series is a series of derivatives. So this becomes 1 plus nx plus n, and you can begin to see the pattern. And I'll even take one more step and say, I'm going to encourage you to commit this expansion to memory. We use it so much in the fields of science and engineering. And so I can stay on task. Let me just give you it. And then afterwards, if anybody wants to chime in the chat and say, hey, can you do that expansion for me? I'll gladly do it. But to stay on task, let me just say that if I did either a binary expansion or a Taylor expansion on something that looks like 1 plus, I would get this. Now, here's why I care about that. The one I want to focus on is m plus little m to the 1/2 power. And the first step I want to do is to write it this way. Let me first factor out the capital M and get this, and then break the power function into capital M to the 1/2 and 1 plus little m over capital M to the 1/2. And so I would say I now have something that looks like the expansion I just gave you, a 1 plus something. What's also crucial in this expansion is that this something, this x, be a small number. And so little m over capital M is a small number. Remember, the point of this discussion here is when little m is much smaller than capital M, but not equal to 0. I'll say it again. If it's so small I set it equal to 0, I run into troubles. So setting it equal to 0 is not going to help. It works great for part B, but as you know, in your limits of your calculus, you can't just set it equal to 0. Sometimes you can, but other times you can't. You got to take the limit. Okay, and that's what I'm trying to do then, is take a series limit of this. All right, but the reason this being small is so nice is if we come back to our expansion, I'm going to be, say, taking this small number and raise it to higher powers. Let's just say this small number is 100th. If I take 100th and I square it, I get 1 over 10,000. So I'm going to justify by saying that this expansion could be 1 plus, and this n is the power it's raised to, so there's 1/2, and the x is little m over capital M. The next term, if I even need it, would be 1/2, and then 1/2 minus 1 over this 2 factorial, and it would be little m over big M squared. And the next term, and I won't even write it down, but I'm trying to say here that I have a strong suspicion that I'm only going to need these first 2 terms, because this first term would be the square root of m, and that's the one that would cancel with that square root of m. And so the second term in this expansion is going to be the one that gives me a non-zero. So I don't need to go to the third one. So I'm don't even need this one. And all these other ones are even smaller still because they're raised to higher and higher powers. So this is the non-zero one. Okay, so keep that expansion in mind. So now I can do the following. I can say the speed is 2 times the square root of L, little m over g. And let me do this expansion. So this expansion we just did would be the square root of capital M times the first term 1, the second term 1/2 little m over big M. The third term, I'm not even going to write down. I don't think I need it, but I'm going to put a plus ... just to remind me that there are more terms. And if I still get a 0 here, I need to go back and keep getting more and more higher terms until the first one is not 0. Okay. All right, so that's the expansion of that. And then, of course, minus this m, capital M to the 1/2. But I can kind of see here then that when I multiply this capital M to the 1/2 times that 1 and then subtract it, those 2 are going to cancel and they'll be left with this second term. So I don't need to go to the third one. So this is the one that's going to give me something that's non-zero. All right, so this would be a 2. This would be the square roots of L over mg. And so now I'm left with this 1/2 and a little m over a capital M. And I won't put, well, maybe one more time I'll put plus ... just to tell me that, hey, that's there. But these are gone. So now I'll start canceling the 2 and not worry about the ... Then I'll have a square root of L from here. And it looks like for little m, this square root would cancel partly and leave the top with just a square root. I would still have a square root of g here, and I would have a square root of capital M. So sure enough, it wasn't an easy mathematical process to get there, but it does match what I was saying here, that the reason, we kind of expect this to be the answer is because if I just ignored the mass of the rope from the very beginning, I would have a non-calculus problem, and I would have gotten this answer very quickly just using algebra. And then, of course, taking the limit should give me the same thing. So sure enough, I do. Yay, and now I'm excited. And so great set of problems, but some real significant math to get us started this morning. So let me flip back over to my Zoom. And I'll make it full screen here. Oh, no, I guess I don't want full screen, and I don't want to exit either. Let's see, how come that's right where I want it to be. All right. And let me go back to the chats and say, wow. All right, now, I spent a long time working on those, and I might have used up the priority list from 102. So anybody, no, let's see, let me just scan down. I don't see a question from 102. I see some good stuff here. I'll read those in just a second here. All right. All right. Oh, yeah, because of the technical difficulties, we probably lost some questions. But Ben, thank you. Don't worry about the technical difficulties. It happens. Yeah, thank you. Did you turn it off and turn it back on? Murphy's Law number 3. Yeah. Okay, Elizabeth, we are experiencing technical difficulties at this time. Ben, I know Droid camera uses USB using. Interesting, and maybe I did this to myself, Ben. What I tried is this morning. I've always in the past just kind of Bluetooth or maybe it's Wi-Fi. I don't really know. No, I think it's Bluetooth. The phone to my laptop. And then this morning I thought, you know what, I'm going to try a USB cable between them. So I was playing this morning, but it didn't seem to connect that way. Now it was nice because it kept charging my phone, but anyway. So I didn't have any luck with that. And then Andrew, I dropped the G. Oh yeah, that's go back there. Good, thank you for letting me pointing that out. Thanks for finding the math professor and the physics application. Good, okay. I think it's the Bluetooth connection. I'm not sure about WebZoom. Yeah, okay. Good. Well, I don't see any other questions. So hopefully, if you guys have one, fire them away. I'll say it again, anybody out there from 102, I'm going to give you a little priority, even though technically our time expired, but we did a massive set of 2 questions here. So I want to get that back to you guys.
Can I ask a question about something earlier in that problem?
Yeah, absolutely.
because I missed when you went over 57. I just wasn't sure where one derivation came from. Let's see. So it was in the very beginning of problem 58 when we were talking about the tension on the rope, and
Yeah.
and we said the tension was equal to the mg plus m1g,
Mhm.
and then we replaced m1 with mu x.
Uh-huh.
What's going on there?
Oh, okay, yeah, I'll repeat that, but yeah, you're right. That's what you would have saw in when we did 57. So let me try that again here, and I'll go back to this. You seem to be okay with this, but it basically what I'm saying is the tension would be equal to all the weight below it, and the weight below it is the hanging mass and then the part of the string, which I'm calling M1.
Up to that
So,
point.
okay, good. So then what I did back in 57, and I'll repeat here, is I did a little proportion. I looked at this string or rope, and I said, well, the small distance below X compared to the whole length of the string would be the same as the small amount of mass below times the whole mass of the string.
Oh, okay.
And so then when I solve this for M1, I put the M with the X over the L. And the M over L is the mass density times X. And I think that's what you're asking.
Totally.
Yeah.
Yeah, that makes sense. Perfect. Thank you.
Yeah. Yeah. Good. Gave me an easy one. After all those hard ones. All right. Anybody else have anyone on those? Because did I see another question come in the chat? No, I don't see another question in the chat. So maybe that was so hard you guys are still digesting it, going, oh my. So
Looks like Hunter did question 22.
oh yeah, okay, good. It looks like Hunter stepped away for a moment. But yeah, I lost that when mine froze out. I lost that part of the chat. So thank you, Daniel. So that was what, 22? All right. So
Yeah, that's what he asked in the chat, but I don't know if you want to wait till he's here or not.
yeah, I'm kind of debating that myself. If there was another question, I wouldn't do it. But you know what?
I had another just like, oh, he's back.
There
But
he
I had
is.
another quick question on the end
Yeah.
of 58. So what we did at the end of 58 was in B, we sort of were able to set big M to 0, and that made it easy for us to find our answer. Then sort of the beginning of C, what you did is you demonstrated what would happen if we were to set little m to 0. But then you sort of, through calculus, showed us that you can't actually do that, and we need to use the Taylor series. Is that sort of the like flow of what we went through there?
Yeah, I would, and I hope my analogy of what you did in your Calculus 150 class helps, because you took a lot of limits in your Calculus 150. And the easy ones are when you say, it says something like, take the limit as x goes to 0. And maybe as an example, if I had like sine x over 1 plus x, how about that? When you say take the limit as x goes to 0, if you don't have any complications about functions that are undefined, you can just set x equals to 0. So in this case, I had something like this. I would just go sine of 0.
Yeah.
1 plus 0 gives me 0 over 1 gives me 0. And I'd go, okay, no problem. But if I had this, if I had sine x over x and was asked to take the limit as x goes to 0, and I put in x equals to 0, I put sine of 0 over 0, which gives me 0 over 0. What's that? And so I run into a complication. And that's not to say that the limit doesn't exist. It is to say that I need to approach this with a little bit of care. And just setting it equal to 0 is not appropriate. And that's what I'm trying to say. So it worked great in B, but it didn't work in C. So I had to come up with another plan. And just to show you this problem, and I would say there's two plans. One plan that you learned in your calculus class was to do L'Hopital's rule, where you took the derivative of top and bottom and then took the limit. But another plan is to do an expansion of this. And that's probably not what you normally did in your calculus class, but let me do that, because if I did an expansion of sine x, I get x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus blah, 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 blah. So then if I divide by the x, this becomes a 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus blah, 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 blah. But then if I just set x equals to 0, I get 1. Yay! And I get something that's not wrong. In fact, it's right. I get the same thing if I had done L'Hopital's rule. If I had done L'Hopital's rule, I would have taken the derivative of the numerator, so I would have gotten cosine x. And the derivative of the bottom, which would have got 1. Then I would have set x equal to 0 and see if I have a problem, which I would have gotten cosine of 0 over 1, which is 1 over 1, which is 1. Yay! So you can approach this in different ways, but you got to be careful. And to be careful when you always just set it equal to 0 or its limit. I picked the limit going to 0. But you set it and see if you run into troubles. And so in B, we didn't run into troubles. Great, we moved on. C, we ran into troubles. So we either had to do a L'Hopital's rule or an expansion. I chose to do an expansion and got the answer.
You don't have to run through all of it, but would it have been possible to solve that using L'Hopital's rule in a different way?
It certainly would have been possible, but I need to go back to the beginning and have a quotient. Yeah.
Interesting. Okay. Cool.
Yeah, definitely. Yeah, that would be a fun exercise to do too. Yeah.
Thank you.
Mm-hmm. Nice. Oh, good. I feel like I'm teaching Math 150. But that being said, that's
Math 150.
Pardon me?
It's been a little while since Math 150, so
yeah, it's been a while. Well, and so what I was going to say is two things. Number one, for some of you, it's been a while, so I consider that part of my job. Is to remind you and teach you Math 50. But also, even when people have taken Math 150 or Math 160 recently, there's just something different about applying the math versus doing the math here. And so I definitely consider it part of the class that what I need to do is to make that transition from, hey, remember what we did in 150. Remember what you learned in 150. Let me show you how you would apply that here. And so that's a big part of this.
Thank you.
I think showing you the calculus is important there. Okay, hey Hunter, you're back. So we were gonna work on yours next. I lost it in the chat room, but you were numbered what, 22?
Yeah. Do you want to do that now, or do you want to do that the next session too? I know that you have breaks too, so
Oh,
I don't want to have you work a bunch. If you need to take breaks.
well, I don't want to leave you hanging. Well, I'll tell you what, if you're gonna be back next section anyways.
I'll be back
okay.
I'll be back for the remainder of the sessions
Oh.
today. So
Okay,
Yeah.
okay. So we'll do that at the next one. Sure. Okay.
awesome.
Yeah.
Cool. Thank you.
All right, guys. So let's call it quits for the moment and take a little break and get something to eat and come on back and see you at 12:30.
See you in a bit.
All right.
Thank you.
You bet.